The following content is supported by victoris.org.
Now we're getting to an interesting example of dynamic programming known as LIS, longest increasing subsequence. A subsequence is a selection of numbers in an array that might not necessarily be contiguous. For example, if the array is as follows, then one possible subsequence is the bolded values over here, 5, 2, 5, 7, 2. Specifically, we see that we have selected some of the numbers from the array and we kept them in the same order. However, they did not have to be contiguous, meaning that 5 was selected over here and 2 was selected, but the number between them, which is 1, was not selected. In other words, a subsequence of an array is just a subset of elements in the original order. This differs from subarray because a subarray has to be contiguous. Now, as a quick check of our knowledge, how many subsequences can there be? The answer is 2 to the n, because for each element, it can either be in the subsequence or can be not in the subsequence. So the longest increasing subsequence is defined as the longest possible subsequence that is strictly increasing. This means that we look at all the possible 2 to the n subsequences, and for each one of them, we want to check whether it's strictly increasing. An example of this would be 1, 2, 5, and 7. A non-example would be 1, 2, 5, 2, because when we go from 5 to 2, it is a decrease in value. However, you can see that for 1, 2, 5, 7, the element to the right is always bigger than the previous elements. So we want to ask, among all possible 2 to the n subsequences, we first select out those who are strictly increasing. Then we want to look for the longest one. If we stare at this array for a while, one can check that the longest increasing subsequence is 4, given by 1, 2, 5, and 7. Now the naive approach would be to iterate through all 2 to the n subsequences, which can be done using bit mask, and each subsequence takes O(n) time to process using a simple for loop. The total time complexity will be n times 2 to the n, which is way too long. So let's try to use dynamic programming to solve this question. So let's try to calculate LIS manually by I power first. What's the longest increasing subsequence ending at this index? The answer will just be 1, because 4 alone is a subsequence and it is increasing. Now, LIS of this index, what is it? It will be 2, because you can see that 4 and 5 is increasing subsequence and it has length 2. Now for this, we can check that the longest increasing subsequence ending at this index is 1, because 4 and 5 are both bigger than 1, so there's no way to construct a longer increasing subsequence that ends with 1. The longest increasing subsequence ending at this index will be 2, and this will be 3, and this will be 2, because we go from 1 to 2, and at this it will be 4, because we go 1, 2, 5, 7. At this index it is 1, and lastly at this index it is 2. Now what structure can we extract from the following example? We see that the longest increasing subsequence ending at this index is 4, and it is given by 1, 2, 5, and 7. Can we observe that 1, 2, 5, 7 is the longest increasing subsequence of length 4 because 1, 2, and 5 is a longest increasing subsequence of length 3, and 7 is bigger than 5. In other words, when we consider the longest increasing subsequence ending at this yellow index, we actually did not need to go through all possible subsequences ending at this index. Instead, we only need to look at all the LIS values and consider which ones we can extend the LIS from. In this case, we can extend the 1, 2, 5 longest increasing subsequence ending at this green index to a 1, 2, 5, 7 longest increasing subsequence ending at this yellow index, because 5 is less than 7. And this 3 becomes a 4 because we've added this 7 to the end of this 1, 2, 5 LIS. So actually when calculating the LIS at this yellow index, we can actually be oblivious to the 1 and 2. We care about the 5 because 5 must be less than 7 in order for us to extend it. And we care about the 3 because 4 is obtained as 3 plus 1. So let's try another example to nail in this intuition. How do you know that the longest increasing subsequence at this yellow index is 3? It is because there is a longest increasing subsequence at this green index ending with the value 2. Because it ends with the value 2, we can extend it to a LIS that ends with the value 5, because 2 is less than 5. And because this LIS ending at this green index is 2, when we extend it by one element, which is 5, it has a length of 3. So what would the code to calculate the LIS at this point look like? We want to consider all possible longest increasing subsequences before this yellow index. And in this case, we want to consider those that have an array value that's less than my current array value, which is in blue. You can see that all these orange boxes are less than the blue box, and this means that the LIS ending at these orange boxes respectively can be extended by appending this 5 to the end of the existing LIS. Now among all these possibilities, which one is the best? The best would be this dark green box over here, because we can see that among 1, 1, and 2, 2 is the longest LIS. So we take 2 plus 1, and that will help us conclude that there's an LIS ending at this yellow index with the length of 3. Putting it more mathematically, right, we look at all the LIS of index j where j is less than I, and the array value a of j must be less than a of I as well. In order for us to extend the LIS, we take the maximum LIS j values, we add 1 to it. So the LIS j over here is in the light green, a of j over here are the orange boxes, a of I over here is the blue box, and the maximum LS of j is the dark green box. So previously we calculated the longest increasing subsequence by I power, but now let's follow the following algorithm. For the first one, the LS of the first index is simply length 1, and that's known as the base case. Then we see that LS of I, subsequently, can be calculated based on the previous LS of j values where j is less than I. So if we consider the LS ending at this yellow index, we consider all the previous LS values that has an array value lower than the current array value. Since 4 is less than 5, this means that the LS ending at 4 can be extended to a LS ending at 5, and we add 1 to the length. Then we continue this procedure. However, we see that for this array value of 1, there are no previous candidates that have an array value smaller than 1. So we cannot extend it from anyone. And so the LS is just itself. 2 can extend from 1, so that's a LS of 2. 5 can extend from 4, 1 or 2. And so we'll take the maximum LS value, which is 2, and add 1, which gives us 3. 2 can extend from 1, which gives us LS of 2. 7 can extend from any one of these, and that gives us a maximum of 3 plus 1, which is 4. 1 cannot extend from any 1, so as an LS value of 1. And 2 can extend from the following 1s, and that gives us an LS value of 2. Now after that, we look at all the LS values, and we pick the largest one, and that is our answer. Do note that the answer is not simply the last LS value, because the LS value at each index is the longest increasing subsequence ending at the index. So if we pick the last one, that means we are forcing our LS to end at the last index, and that is not what we want. Here's the following code. We create an array called LIS which has size n. Then we have a for loop that calculates all the LS values. The default value for LIS is 1, but we'll try to increase this value by considering all the possible candidate LS to extend from. So we have another for loop that goes from j equals to 0 to j before I, and for each one of them, if our a of j is less than a of I, that means our LIS ending at j can be extended to our LIS ending at I, and hence we try to maximize LS of I by taking the max of itself with LS of j plus 1. Effectively, the following for loop takes the maximum value of LS j plus 1 among all the j less than I and a of j less than a of I. Finally, we calculate the answer by taking the max of all the LS values, and we output it. Here's a question that you can attempt for LIS. Next, we'll talk about the coin minimum problem.